Larry, thank you very much for that kind introduction, and I want to thank the Technical Program Committee for the honor of the invitation to present this paper and for the honor of talking to you tonight. What I'm going to talk about, anytime you give a plenary talk, it's an opportunity to kind of take an expansive view of the field, and I want to talk a little bit about where wireless communications I think might go in the next decades, and in order to do that, sometimes it's fun to kind of look backwards as well. And so this is the press release. About 40 years ago, Marty Cooper made the first cellular phone call from Manhattan, in 1973. And so here's a picture of the original Dynatac phone. Some of you, oldsters might remember this from the mid-70s. And if we look back at the press release from that time period, it's really a pretty humorous historical document. They talk about as many as 2,000 transistors on one small piece of silicone, and the size of a large pinhead. And then they kind of hint that further applications of this technology will produce even smaller portable phones at lower costs. And the great industry papers that we see outside this room tonight are kind of an illustration of how far the technology has come in the last 40 years. And I like to think about some media from the 80s that kind of illustrates this. And one of the things that I think is funniest is, Wall Street, and there's Michael Douglas out on the beach in Long Island. And he's at that time in 1987, my gosh, he was so rich. He's like this Wall Street investment banker. He had an actual cell phone in 1987. And that's sort of what it looked like then. And so obviously we've come an incredible way in the intervening 30 or 40 years. And, today we're at the spot where really just about every person on the planet who could have a cell phone pretty much probably has one today. The number of cellular subscribers is over 5 billion. There are 7 billion people on the planet. So, infants don't have cell phones, but most of the rest of the adults in the world do. And we sell well over 1 billion cell phones every year, on a worldwide basis. So our goal for those who started this industry 40 years ago, the goal was to give every person on the planet an opportunity to communicate with any other person on the planet in a low-cost way. And I think that we've kind of achieved that now. And so we're now at the point where we're thinking about, well, how much, can we stream video to every phone? And, what kind of new apps can we create that take advantage of the bandwidth capabilities of the technology? But in terms of sort of fundamental demonstration of our capabilities to enable mass communications to every person on the planet, we've achieved our goal, I think. And so the question then sort of arises, well, what's next? Like, what can we do with this technology that will really enable future economic growth and future human betterment, over and above what we've achieved so far? And, really there are a couple of things that have kind of, so when we ask this question, then we have to think, well, what technology advances will enable these further developments? And of course, one of them is Moore's Law, and Moore's Law is continuing, and ever more creative ways are being developed to pack more and more transistors onto a single piece of silicon. High K dielectrics and strain channels and all the things that are being done. And the number of, I expect the number of transistors to continue to rise, over the next several decades through, increasingly clever kind of fabrication approaches. And then the second thing that's really enabled this is Metcalfe's law. Metcalfe's law is a networking concept that basically says that the value of the network is roughly proportional to the square of the number of people or the number of nodes on the network. And of course, the more people that we connect to the network, the more value the network has to those who use it. The classic example of this is like a fax machine, right? The first fax machine was completely worthless, but once there were 2 fax machines, then the network had some value. So so I think these two trends, Moore's Law and Metcalfe's Law, are continuing to expand and continuing really to change everyone's lives. So that then, though, leads to the question, how can we use Metcalfe's Law and Moore's Law to continue this advance in human development? And I think one way to take a look at this is to look at, what are the major health challenges that confront humans as they go through their lives. And this is a summary of a report from the World Health Organization from, how has humanity changed from 1990 to 2020? What are the major drivers of human health problems? And the things that come up here in the next 10 years are heart disease, ischemic heart disease. That means coronary artery blockages, road traffic injuries. More and more cars are being deployed all over the world now. It's not just a Northern Europe and United States issue. And other things that historically through mankind's history, like war and tuberculosis, are moving down the scale. So, of course, we all want to communicate with each other. That's why cell phones have become so popular. But we also want to live long and healthy lives. And so perhaps there's something that wireless can do in this realm as well. So let's take one example of an area where I think like RF will have increasing impact in the coming years. And this is an example of this is a small startup company called CardioMEMS, which is a MEMS company. I think it's from Georgia Tech. And as I'll explain in just a second, they've been working on ways of reducing the incidence of heart failure of at-risk populations. And basically, these are some statistics that I show here that of really the economic burden that heart disease has, at least here in the United States. About $40 billion a year of direct cost for heart failure is attributed to heart failure issues. And it costs, roughly $250,000 to treat someone in their final 2 years of life if they have heart issues. And so it's actually kind of interesting. If you have a history of heart disease, it's been shown that if you can monitor the pulmonary pressure, basically the pressure in your pulmonary artery, that this is an early warning signal of future problems. And actually this future warning signal can happen several days to even several weeks before the physical symptoms get dramatically worse that you actually would notice them. So the theory is that early intervention, if you could monitor pulmonary pressure, the pressure in your heart, if you could monitor it early on a very regular basis, you could perhaps detect these early warning signals and really reduce morbidity. And so this company, CardioMEMS, has a MEMS implant that basically does real-time monitoring of pulmonary blood pressure inside the body. And it actually just received FDA approval a few months ago. And basically, it's a very simple little MEMS device that it's just a variable capacitor pressure sensor. And it's put in parallel with an inductor. And so the capacitor and the inductor resonate at a certain frequency, and that's tied to an antenna. And of course, as the pressure varies, it's a pressure-sensitive capacitor. So as the pressure varies, the resonant frequency of the tank varies as well, and you can use this as a very, very sensitive pressure monitor of the heart. If there's an external RF source that's kind of beaming into this area, you use near-field coupling to detect the change in the resonant frequency. And so typically what would actually happen, you can kind of see it there in slide C, is that the RF source would be like built into a pillow or something that you'd lie on to do the measurement. And so here's at the bottom are some real-time graphs of mean blood pressure as a function of time for a typical patient. And what's really cool about this is that they've actually done a clinical trial with this device. They implanted these blood pressure sensors into the heart in a fairly large trial. And there were two different populations, actually. The entire population had the implant, but only half of the population was subsequently monitored. And what you can see here on the left is the left, oh, I'm sorry, let's go back. The left here is a plot of cumulative hospital admissions for two groups, the control group, which is the blue curve, and the group that that had been monitored, which was the red group. And you can see the cumulative admissions have dropped quite substantially. And the curve on the right is a likelihood that you end up in the hospital. And once again, the blue curve, which is the curve that has the heart implant and monitor, has dropped fairly dramatically. So this is an example of how real-time monitoring of some aspect of the behavior of the heart, wireless, I should add, wireless monitoring of the behavior of the heart, can lead to very, very significant clinical outcomes for patients. And the result of this, of course, is reduced healthcare costs. So this is, I think, a great example of the kind of device, the kind of opportunity that RF is going to have in the coming years to really have a major revolutionary impact. I'll give you several more examples like this. Another one, this was something that EPFL announced last year in 2013. This is a press release that they announced, but basically This is something that's a little bit different. It's a Bluetooth device that's small enough to be implanted, and it has a bunch of chemical sensors on it. And once again, if you have heart problems, sometimes your heart muscle begins to die a little bit before you have a heart attack. And if you have a sufficiently sensitive chemical sensor inside of your body, you can measure those chemicals, and you could send, like through Bluetooth and Wi-Fi, a little alert, hey, your troponin levels are rising in your blood, you may be about to have a heart attack. And so this is another example of an implanted sensor inside of a body that can give us an early warning of possible adverse health outcomes and of course if you can catch a heart attack early, you can prevent a lot of further problems. Another great example is, once again, this is something that was just FDA approved several weeks ago. Sleep apnea. Sleep apnea is a huge problem in this country, where people their larynx gets choked off during sleep, and you actually start to you can't breathe because your throat is obstructed. And it's a muscular problem. It has to do with loss of muscle tone in the throat, and there are weight issues, and but it's a very, very big problem. And there are many fairly onerous solutions for sleep apnea. But this is a very simple once again, it's an RF-based system. There's a sensor that's implanted inside of your diaphragm to measure your breathing, and then there's a little transceiver that's implanted in your chest, and there's a stimulator that goes to a nerve in your neck, and actually if the system detects that you stop breathing, it sends a little electrical impulse to the nerve in your neck and opens up your breathing passageway. And once again, clinical trials have demonstrated that this implant has a very, very significant improvement in the sleep performance of people with sleep apnea. And this device is implanted into the chest. It's recharged wirelessly, and there's a Wi-Fi connection that will connect to the internet that allows real-time monitoring of the sleep by the patient's doctor. So once again, another example of implantable biodevices that can lead to pretty dramatic improvement in patient health, and they use RF technology as one of the key enablers. So as Peter mentioned earlier in his previous talk, this is a field that's kind of called the Internet of Things. And the Internet of Things is not person-to-person communication, it's person-to-machine communication, or in some cases machine-to-machine communication. And it opens up an entirely new opportunity for RF and wireless communication technologies of all kind. And not just in the health field, but in transportation and environment and energy, just all kinds of different possibilities. In fact, it's I think as revolutionary in its eventual potential outcome as what the cellular revolution was 40 years ago when we started down this path. So there are, of course, people have jumped on this in a very big way in recent years, and there are a lot of different potential kind of air interface technologies for the Internet of Things applications, some of which are very, very, very short range, very, very low data rates like the NFC, and some of them are sort of Wi-Fi based. There's the 802.11ah standard, which is coming along, which is a very wide area, very low power Internet of Things kind of Wi-Fi technology specifically built for this applications. For this application, there are proprietary technologies. There's Zigbee, there's Bluetooth. There's white space communication, so there's no one air interface standard or frequency that's been determined yet for these applications, and so it's a very fertile ground for a lot of experimentation. There's some kind of interesting things, though. There's a company called Sigfox, which is located mostly in Europe, although they're rolling out a network in Silicon Valley now. And Sigfox basically builds a dedicated network just for the Internet of Things applications. So rather like Verizon or AT&T would roll out a cellular network, here in this country, Sigfox will roll out a Internet of Things network just for these applications. And once again, this is a dedicated network at dedicated frequencies for Internet of Things applications, which are very, very, very low power, and and at the same time very, very low bit rate, like 100 to a kilobits per second. So there are opportunities not only for unlicensed spectrum use, but also licensed spectrum use in very dedicated manners. Now, the next opportunity that I want to kind of mention is something that this slide sort of captures. And let me talk just a little bit about this. So when we start to connect things to other things, the number of things that will be interconnected is going to start to grow very, very fast. You know, right now we have about 5 billion people on the planet connected to each other through the wireless infrastructure. So maybe there are 10 billion internet connections on the planet. But as we start to embed wireless devices into people's bodies, as we start to put them into cars and other types of manufactured objects, the number is going to grow exponentially. And this gives us an opportunity to do some really interesting discovery using big data analytical kind of techniques. And in particular in the health field, the use of the Internet of Things combined with big data, I think provides us a really rich opportunity to once again uncover some interesting health opportunities. So this is a paper that was published in 2013 by researchers at Microsoft, and basically they used just web search data, people just clicking on their computers web searches, and they looked for specific interactions between drugs that had not been thought to interact before. And in fact, you know, so if someone will type in, I'm taking this drug and I'm feeling lousy, you know, what's going on here? And so actually a web search uncovered a really profound interaction between two drugs that had not previously been thought to interact with each other, paroxetine and pravastatin. Paroxetine is an antidepressant. Pravastatin is a cholesterol-lowering medication, you know, for people's hearts. And what it found was that these two, this is uncovered just through web searching, that these two drugs created hyperglycemia, which is a precursor to diabetes. Right, so this is two drugs that had not been thought to interact with each other, but basically through big data were, you know, discovered to lead to hyperglycemia. And I think that as we start to really get more and more fine-grained, very, very fine-grained health data, the opportunity for learning rapidly about better treatment methods and possible adverse effects of drug interactions is going to really be dramatically improved. So this is, I think, a side benefit to this Internet of Things that we're just now beginning to understand. It's actually a really exciting kind of opportunity. So let's talk about a couple more of these Internet of Things applications in the health field. Here's a great example from Brian Otis, who is now at Google, was at the University of Washington before, and here is a contact lens-based glucose detector. And it's all done using RF power and backscatter communication. And you know, we all know about the explosion of diabetes in this country and other countries as well. And typically people have to prick themselves to do a blood test. And that's very, you know, difficult and expensive. And so is there a better way for people who have diabetic conditions to monitor their blood glucose? Well, it turns out that your saliva, although the concentration isn't as high in your blood, the concentration of glucose, it's still pretty good. You can actually monitor glucose fairly accurately using saliva. So some people are looking at kind of spitting into a test tube or something. But if you could use a contact lens, which is in direct contact with your eye, that would be great. That would really be great. So that's something that these researchers reported on. And there are many different aspects of this. And I think this is a good example of the kind of thing we may be building in the future. There's a sensor, which is a glucose sensor, which basically involves oxidation of glucose, and then you use the oxidation reaction to drive a current generator. And that sensing of the glucose is then combined with a simple RF circuit, a simple backscatter RF circuit, to which you know, takes an input RF power, converts it to DC, starts up the sensing circuit, and then backscatters the information back to the it's basically a passive RFID kind of application. And so, and of course, if you could just plop this into your eye if you're a diabetic every morning and you periodically test yourself maybe with an iPhone, this is vastly superior to a prick of a finger to measure the blood. So once again, a great example of potential health, you know, a really kind of transformative healthcare application using RF. Another great example of using RF for these types of applications is work that Ali Hajimiri has done at Caltech. And here the idea is that we use these magnetic particles. They're tiny little magnetic beads, several microns in diameter, and they're usually labeled with some kind of biological thing. It might be like an antibody, or it might be some kind of compound that bonds to a specific DNA. And what Ali has shown, I think, very nicely is that so then you want to measure the presence of these magnetic particles. How do you do it? Well, in this case, what we do is we take an RF oscillator and we measure the change in the frequency of the RF oscillator as a magnetic particle lands in the vicinity of the inductor. And of course, you know, if one of these magnetic particles lands on the inductor, the magnetic energy that's stored gets a little bit higher. It changes the frequency very slightly, and that change in frequency can be measured very, very accurately and determine the presence or absence of one of these particles. So, and in fact, you know, Ali showed that you could get sort of, you know, sub-ppm resolution, you know, really, really, really fine frequency resolution if you integrate long enough. And so, you know, even measuring the presence of a single one of these molecules is possible using these techniques. Once again, it's an RF technique. We're measuring frequency, which is something that we all know how to do. It turns out it has a remarkably effective bioassay kind of application. And then I'd like to talk a little bit about maybe sort of the ultimate in interesting implantable applications is the work, some of the work that has been done at a variety of labs on brain-machine interface. And it's something that I've been working on with some of my colleagues at Brown. And basically the idea here is to enable communication between your brain and some kind of prosthetic limb for people who have lost a limb or victims of locked-in syndrome or extreme Parkinson's or some forms of epilepsy as well. And if you could actually measure the neural signals in your motor cortex, you could use those signals to control the motion of various prosthetic limbs. And so this is a kind of a far-out application. I don't expect this to be happening next year on a widespread basis, but in 10 or 20 years, the technologies have moved actually quite rapidly, and we're getting to the point where clinical trials are in place to do this kind of thing. Now, in this case, the challenge for RF is actually a very profound one, because you want to measure thousands of neurons in the motor cortex, perhaps even tens of thousands of neurons. Each one of them is in and of itself, you know, rather low speed, maybe, you know, 10 kilohertz or something. But since you have 10,000 of them, or even more, the data rates that would be coming off of your head of these neural signals can be in the order of gigabits per second in some cases. And you would really want this interface to be a wireless interface, because having a cable coming out of your head, which is actually how the early clinical trials have been done, is not very satisfactory from a user perspective. So we've been working on and several other groups have done this as well, fully implantable wireless devices that can read out hundreds of neural signals, you know, at a time in parallel, and then use this information to control the movement. So this is an example of one of our devices. It's in a titanium enclosure with a sapphire lid. It's inductively charged, and then there's a pretty sophisticated wireless link to take the data out of from the neural signals in the head out to the outside world. And you can see sort of at the top right, there's the array actually, which is pressed into the motor cortex. It sounds like a very drastic surgical procedure, but for people who are profoundly disabled by loss of use of movement, this is actually an incredible breakthrough. So here's an example. This is a 100-element array that we've been testing and with our wireless devices. And so you can kind of see the neural signals that are coming out of this measurement. And you can also see that not every channel is always addressed properly. Sometimes you do the implant and you don't catch every neuron. So there's quite a bit of kind of error. There's quite a bit of redundancy that has to be developed in these signals in order to get a good result. And the kinds of, so what you actually have with this data is a bunch of just neural spiking data. And somehow you have to translate that into intentional movement, a movement of an arm and a rotation of an arm. And so there's quite a bit of signal processing and, you know, machine learning that has to go into this. And so here's some typical examples. We take that neural data and we resolve it into two principal components. And it turns out that these two principal components are sufficient to measure things like turning of the head or grabbing of the apple or itching the face. Each one of them has a kind of a unique signature that we're able to detect. And so this technology, I think, is going to rapidly advance over the next several decades, because our understanding of the relationship between neural signals in the brain and our intentional actions is getting better and better all the time. And then wireless, our ability to take gigabits per second of wireless data in a very low power way outside of the head, outside of the human body is improving dramatically as well. So I think it's a really exciting time to be doing this. So I've kind of gone through the whole gamut of biological applications of, or biological kind of things that we want to do, sense or test or whatever. And this is a really kind of a summary. There's electrocardiogram, the blood pressure, respiration rate, oxygen. It'd be great to have a CO2 sensor to measure CO2 in a very low cost way. Heart rate, blood glucose. There's just almost an infinite number of things that if we could measure in a very low cost and robust way would, I think, lead to dramatic improvements in human health over the next decades. Now, in order to do this, we need to somehow power these sensors. And I've kind of skipped over this problem, but it's a really a pretty big problem. And you need some kind of energy source. So in some cases, these are passive devices. They take in RF, they're like a passive RFID application. They take in RF energy, and they wake up, they do something, and then they spit it back. But there are other opportunities as well. Acoustic noise, piezoelectric approaches. Solar, of course, is a classic. But these are all in the domain of very, very low power, very, very small form factor types of applications. And there's some very creative things that you can do in the biological space. This is an example of a glucose fuel cell. And basically what you do is you take glucose and you oxidize it. And you oxidize it at the anode and you reduce it at the cathode. And so if you have glucose running around in your body, you can build a very nice little fuel cell with glucose and oxygen. And of course, inside the brain is just bathed in glucose. That's the energy source for the brain. So glucose is a potentially very powerful source for brain-based electronics. And you can get up to about 180 milliwatts per square centimeter of peak power using glucose-based sensors. So I think even these kind of exotic things that we don't normally think about in the microwave realm may be very good for these Internet of Things applications. Ada Poon's group at Stanford has done a lot of really nice work recently on delivering focused RF power into a patient's body. Much deeper than we thought would be possible previously using sort of mid-field approaches. And Peter was talking earlier about cooking things. So one of the things that we have to be careful about when we deliver RF power into the body is we don't cook the body. And so this actually, Professor Poon's group has achieved, I think, really good results in delivering 1.7 gigahertz into the body. But the results, I think, still kind of illustrate the potential problem. It takes about 500 milliwatts of delivered power to, delivered power into your chest to reach about 500 microwatts of power deep, like say at about the level of the heart. So the other, 499.5 milliwatts is sitting inside of your chest, just cooking the chest. And that actually still is within safe power limits, but if we start to put too many of these devices inside of our bodies, RF power limits are going to start to become an issue. Now, if we put a lot of RF power into the body and we use that RF power to create the DC power that's necessary to run these devices, then the issue of RF to DC efficiency becomes a major limitation. And the problem that we encounter with RF to DC power conversion is that the efficiency is not very good except at rather high powers. And in fact, most of these devices that we're talking about for Internet of Things applications are, have minus 30 to minus 60 dBm of received power inside the body. And you can see that at those power levels, the efficiency has dropped very low to the 10 to 20% range. So one big breakthrough that I'm hoping we could see at this conference in the coming years is a real improvement in RF to DC efficiency as the input power level drops. So there are a lot of other, I've just talked about health applications so far, but there are, I think, equally transformative applications in many other realms for the Internet of Things. For smart grid technology, for smart environmental sensing, these are all applications where a networked world will allow us to be more intelligent in how we use the finite resources that we have on the planet. I think another great application of the Internet of Things is in the transportation field. And I'll just speak very, very briefly about that quickly. You know, car fatalities, at least in the United States, have fallen quite a bit. And actually the recession in 2009 really caused them to drop off dramatically. But they're still too high. You know, we still lose about 30,000 people every year to traffic fatalities. The fatality rate has dropped very nicely, but the number of people killed in automobile accidents is still really, really way too high. And of course, we've been talking for many, many years at this conference about automotive radar and adaptive cruise control. And the next, you know, the next kind of generation of that is vehicle-to-vehicle and vehicle-to-infrastructure applications. And the national, which are once again now making the car, you know, completely hooked up to the internet and the infrastructure that surrounds it. And you know, the National Highway Transportation Agency estimates that about 80% of all crashes could be, you know, reduced or even eliminated through widespread deployment of vehicle-to-vehicle and vehicle-to-infrastructure technology. And then the final thing, which everyone knows about, is this Google self-driving car, and there are several other versions of it out there. And this technology has really come a long way in the last few years. And so there are a couple of things that I think are very interesting from a wireless perspective on this. First of all, every car is generating about 1 gigabit per second. And what you'd really like to do is take every one of those bits back to the mothership, right? And have the mothership at Google, you know, churning on the data and improving the algorithms all the time. And if you're able to do that, every car that's on the road is actually able to be the best car that there is, because all cars have access to continuously updated data and continuous improvements in performance and reliability. So the potential for, I would say, radical reduction of this traffic fatality rate that we've all been living with for all of our lives is, I think, really truly on the horizon, maybe not in the next 5 years, but in the next 10 to 20 years potentially. So in terms of looking at this conference, how can we make a difference here in this opportunity? I think there are many, many enabling technologies for the Internet of Things that are right at the heart of what we do in this conference. Of course, single chip radio. I mentioned efficient RF to DC integration, low-cost integration of sensors with electronics, energy storage in a small form factor. How can we store a sufficient amount of energy to run these devices? How can we deliver energy? It could be RF energy or acoustical energy safely to devices inside the body. And then form factor and jammer interference. The smaller the devices, the better. And then there are some economic challenges as well. There are both challenges and opportunities, right? So let's think about healthcare for just a second. So we talked a lot about the potential of this Internet of Things technology to have dramatic improvements in human health. And actually, you know, healthcare reform, at least in this country, may require that you do that. You know, if this, for example, if this cardio-MEMS system really does reduce the incidence of heart failure for people who've had a prior incident, wouldn't almost everyone who's had this be a candidate for the surgery? Similarly with cars, you know, I can imagine, and I think this is on the horizon, that regulators may require vehicle-to-vehicle and vehicle-to-infrastructure communications for all new cars. For both of these cases, both for the healthcare and the automotive industry, the cost-benefit analysis, which is what's going to be driving a lot of regulation in the future, is really positive. Now, there are many, many roadblocks as well. There's the liability issue for the intelligent transportation. There's network infrastructure issues for Internet of Things in general. Privacy concerns, I haven't talked about that, but if Google is now taking every bit of not only our web surfing data, or the NSA, I guess, you know, the web surfing data or our personal data, now what happens when our medical data is also part of the cloud, and what are the privacy concerns there? I think this is an unsolved issue from a societal perspective. And then FDA approval for a lot of the medical applications is very, very slow. It can take years for FDA approval, tens or even hundreds of millions of dollars for certain types of devices. And of course, FDA approval is important because it guarantees the safety and health of the patients, but the long-term, it really slows things down very much in the long term. So I'd like to sort of conclude by saying that I think that this community at the RFIC Symposium has a really unique opportunity in the next decades to have a significant impact on this new communications technology, just like we really enabled the cellular revolution and the smartphone revolution in the last 40 years. I think we will be the enabling technologists for the Internet of Things in the next 40 years. And continued research is needed in a lot of areas. It's a very exciting field. Sensor technology, energy storage, harvesting, security, wireless sensors, all of these hot areas require really deep thought and development. And if we do that, I think that we can really fully take advantage of this, this opportunity. So I'd like to thank many, many people who've helped contribute to this talk through various conversations and discussions. And I want to thank you once again for giving me the opportunity to talk to you tonight. Thank you.